In this video, we're going to see effect of temperature on diode's IV characteristics. Current flowing through the diode, ID, is represented with respect to the voltage applied across the diode, VD, by this equation, which we call the diode current equation, where I0 is given by this equation, and eta is called the ideality factor, which is approximately 1 for germanium diode and 2 for silicon diode. ID versus VD plot would look like this. In this region where VD is positive, we call this as an forward bias, and when VD is negative, this region, which is called in reverse bias. Forward bias plot is in the first quadrant and reverse bias plot is in the third quadrant. To show you the magnitude of I0, I have exaggerated the figure, so this figure is not to scale. This magnitude of current is I0, which is called as the reverse saturation current. As these are the IV characteristics of the diode, now let us see how temperature plays a role on these IV characteristics. To start with, let us analyze the reverse bias condition first, and then we will move on to forward bias condition. Let me rewrite this current equation. Under reverse bias, this VD would be negative. We can rewrite this expression as ID is equal to I0 times e power VD over VT minus I0. And as it is in the reverse bias condition, we can say VD is negative, and if VD is less than minus 3 VT at least, then we can pretty much neglect this term compared to this I0. As a result, we can say under this assumption that ID would be is equal to minus I0, which wouldn't be changing with respect to applied voltage. That's why we have shown the current characteristics here in reverse bias, that the current is constant, which is not changing with respect to potential applied. And for a very small voltage that is applied in reverse bias, there is an increase in the current in the negative direction, but as we increase beyond a point, it doesn't change, it is constant. That is when this exponential term is neglected. Now our intention is to find how is this diode current in reverse bias impacted because of the temperature. So in order to find that, we need to find del ID over del T, where T is the temperature. So in order to find that value, we need to first understand what is I0. As we know from here that I0 is given by this expression, where this Pn0 is given by Ni square over Nd, because Pn0 is the minority carrier concentration on N side, which is given by Ni square over Nd, the doping concentration on N side, and Np0, which is minority carrier concentration on P side, given by Ni square over Na, where Na is the acceptor concentration on P side. Now we can rewrite this expression of I0 like this, and we know the expression for Ni square, which we have derived in previous videos. So Ni square is given by some constant C, which is independent of temperature, times T power 3 times e power minus of Eg over Kt. Now Ni is a strong function of temperature and energy band gap. So does the I0 now, because I0 depends directly on Ni square. So which means I0 is a strong function of temperature. And we can see another observation that as it depends on energy band gap, if the energy band gap of the semiconductor is very less, then I0 would be very high value. And if Eg is higher, the I0 would be less. I0, apart from reverse saturation current, it is also called as leakage current. If Eg is higher, we would have less leakage current. Now you can understand, in terms of leakage power, silicon is a better semiconductor compared to germanium. Now substituting this Ni square into I0, we can write I0 as this constant times C, let's say is C prime, times T cube times e power minus Eg over Kt. Now differentiating this I0 with respect to temperature, we can write del I0 over del T is equal to C prime times 3T square times e power minus Eg over Kt plus T cube times the differentiation of the exponential, which would be e power minus Eg over Kt times minus Eg over K times differentiation of 1 over T, which would be minus 1 over t square. So minus minus cancel. And we can rewrite this expression as c prime and taking t cube and e power minus eg over kt as common. Then we will have 3 over t plus eg over kt square. And we know this quantity is nothing but I naught. So we can rewrite this again as I naught, and let me take the t outside. So we have I naught over t times 3 plus Eg over Kt. This is for del I naught over del T. If we calculate this value for germanium at room temperature, where T is 300 Kelvin, and for germanium energy band gap is 0.66 electron volt at room temperature. If we substitute the values in this, we would get a value of 0.095 times I naught, which means I naught is increasing at a rate of 9.5% per degree centigrade at room temperature 300 Kelvin. But it has been practically found that the rate at which the reverse saturation current increases per unit degree centigrade for both silicon and germanium is 0.07, which means this converts to 7%. We can say that del I naught over del T is equal to 7% of I naught, which tells us that the reverse saturation current increases by 7% per degree centigrade. To understand this better, let's say at T is equal to T1, I naught is I naught 1, and T equals to T2, where T2 is T1 plus, let's say, 10 degrees centigrade, then it is I naught 2. Then we can find the relationship between I naught 2 and I naught 1 by using I naught 2 is equal to I naught 1 times 1 plus 7%, which is 7 over 100, whole power 10, because we are having 10 degrees centigrade increase. This would be approximately equal to 2 times I naught 1. Which means we can say for every 10 degrees centigrade increase in temperature, the reverse saturation current doubles itself. This formula is very similar to the cumulative interest calculated, and it is exactly the same. The current increases 7% and the basic also keeps with it, and every degree centigrade it keeps the same increasing. So that's why we use the cumulative interest formula here to find. So bottom line in reverse bias is the reverse saturation current doubles for every 10 degrees centigrade. Let's say this is for T is equal to T1, and for T is equal to T2, if we represent I naught, it would be somewhere here, where this value would be new I naught, which is I naught 2. Let's say this is I naught 1, which means as temperature increases, the reverse saturation current increases, and that too specifically it increases 7% per degree centigrade. Or we can say in other words as it doubles for every 10 degrees centigrade. Now let us see how temperature impacts the forward bias characteristics. Let me take the diode current equation. As we are in forward bias, Vd is positive. If Vd is greater than or equal to 3 eta Vt, we can neglect this minus 1 term because the exponential term would be far greater than 1. So I'm approximating this to be I naught times e power Vd over eta Vt. We can rearrange the terms to write the expression for Vd like this. Now we are interested in finding what is del Vd over del T. Now we can find this if we assume that the current that we are applying through the diode is constant. So let me represent pictorially here that we have a current source. Let's say current we are applying is I, and we are enforcing the current to flow through a diode. So then the current is actually fixed. Let's say current that we are fixing is here, which is I, and at this point the voltage is, let's say, V1, and this curve is for T is equal to T1. Now let me find the differentiation of this, which would be equal to minus eta times differentiation of Vt, which would be K over Q, because Vt is Kt over Q, differentiation of it with respect to T would be K over Q, times ln of I naught over Id plus Vt times differentiation of the ln term, which would be 1 over I naught over Id times differentiation of I naught over ID, which would be nothing but 1 over ID, as we are assuming ID is constant, and del I naught over del t. Now ID would get cancelled, and in fact we know the expression for del I naught over del t, which is given by I naught by t times 3 plus Eg over kt. We can substitute this expression into this equation. This can be rewritten as like this, and it can be still further reduced to Vd over t minus eta Vt over t times 3 plus Eg over kt. If we take some practical values and substitute in this equation, we would get the variation of Vd with respect to temperature. So let me take practical values like temperature is 290 degree Kelvin, ID is 10 milliamperes, I naught is 1 picoampere, and let's say eta is equal to 1. In that case, this expression would come out to be approximately minus 2 millivolt per degree centigrade. And for silicon, it seems practical measurement shows very close to minus 2.5 millivolts per degree centigrade. So from now on, we would take the variation of voltage across the diode with respect to temperature as minus 2.5 millivolts per degree centigrade. So which means, assuming a constant current through a diode, if temperature increases by 1 degree centigrade, then the voltage across the diode would decrease by 2.5 millivolts. Let's say now T2 dash is T1 plus 1 degree centigrade. Then let us see how the forward bias characteristics would look like. It would look something like this for T2. I've exaggerated this to show you the difference. This figure is not to scale. So if I project this value, I would get the V2, which would be 2.5 millivolts away from V1. But V2 would be less than V1, as this equation suggests that the voltage across the diode would decrease when temperature increases. Points to note that the reverse saturation current would increase by 7% for every 1 degree increase in temperature. And similarly, we can say for every 10 degrees centigrade increase in temperature, I naught doubles. In forward bias, we can see if a diode is forced to conduct a constant current, and if we increase the temperature by 1 degree centigrade, the voltage across the PN junction diode would decrease by 2.5 millivolts. Another simple way to remember this, as temperature increases, the forward bias characteristics would shift leftwards, and the reverse bias characteristics, they would shift downwards. In fact, this diode current equation doesn't model the breakdown phenomenon in PN junction diodes. So in next video, we will see the breakdown phenomenon in PN junction diode and their temperature dependence as well.